Having discussed a bit about the structure of the periodic table, we're now going to move into talking about chemical bonding. And we're going to begin that discussion with a discussion of ionic bonding. But before that, you may recall that we've talked about electronegativity and ionization energy as measures of atoms' tendencies to gain or lose electrons, and that those tendencies can be predicted based on their location on the periodic table. In particular, we learned that noble gases have exceptionally stable electron configurations. And so atoms tend to gain or lose electrons, at least those close to the noble gases, in order to mimic those noble gas electron configurations. One of the ways that we identify these trends is by looking at what are called valence electrons. Valence electrons are the electrons in the highest occupied energy level for an atom. Be aware that this is energy level and not sublevel, so we're looking at numbers, not S's and P's. The second energy level is both the 2S and the 2P. And in particular, we're going to look at representative elements, or the group A elements, which we labeled on our periodic tables. Representative elements are filling S and P orbitals in their highest occupied energy levels. The other thing we know about representative elements is that elements in the same group have the same number of valence electrons. That's the whole organization of the periodic table. It's there to mimic the Aufbau diagram, and so groups are set up because they have the same sub-level configuration. For instance, the third row in the P block all end their electron configuration with something P3. Here we have our periodic table. The stair-step line there is going to separate our metals from our non-metals, and the general rule with gaining and losing electrons is that non-metals are typically going to gain electrons to get to those noble gases, whereas metals are typically going to lose electrons. And then again, we need to keep in mind S and P sublevels being filled are our representative elements, and so the representative elements are both that S block and the P block. And so what we're going to look at is the stability of various electron arrangements, and in particular, what represents a stable versus an unstable arrangement of electrons. There are a bunch of ways to think about this. So electrons can be arranged in a bunch of different ways, much like the blocks on this screen can be measured in a bunch of different ways. On the left represents a stable arrangement of the blocks. We let those blocks rest on top of each other like that. We can bump the table and not, expect those to go tumbling down. They may fall, but it's just as likely that they'll stay in that configuration. Whereas the configuration on the right, if it is just so balanced that friction is allowing those things to hold together in that arrangement, and the center of mass is over that block on the bottom, that arrangement can happen, but it's a highly unstable arrangement if you can manage to get them to sit like that. Any little bump, breeze in the room, and they're going to fall. So that represents an unstable arrangement of the same blocks. Another way to think about this is in terms of a hill. So here we have, if the ball is resting on top of this peak, you can potentially get it to rest on that peak, and yet you have an incredibly unstable arrangement. Any shift in energy, and that ball is either going to roll to the left or the right. Whereas all the way at the bottom of the hill on the left here, we have a very stable arrangement. Unless there is some massive input of energy into that system, you are not going to be able to change the position. And any little bit of energy that might cause it to move up the right or the left slope, as soon as that energy is depleted, it's going to roll back down into that position. And of course, we might consider that you have this place where the ball is somewhat rested in some form of intermediate stability, where it's not your lowest possible energy, but not your highest possible energy, but some kind of intermediate resting point. For electrons, low energy is filled S and P sublevels. If your S and P sublevels are filled something S2, P6, then you have the most stable arrangement. That's the ball at the bottom of the hill. If you have half-filled sublevels, P3, for instance, then you have that kind of intermediate arrangement. And again, same thing with your d and your f orbitals. 5 electrons, all with the same spin in a d orbital, is an intermediate stability. Same thing with the F's. Half-filled sublevels and completely filled sublevels are intermediate stabilities between those S's and P's being completely filled, which is the best arrangement for electrons.